Okay, we're going to rewind. Welcome back to the live. Good afternoon, Safa. How are you doing? 3 to 11H, how are you guys doing today? We are going to actually start our lesson on calculations for this particular chapter. And these are the things that you guys will see in a chapter of your chemistry book that deals with solute calculations. Now, here is the thing. There is a lot of math involved because you've got to be able to read the problem and all that good stuff. But more importantly, you want to make sure that as you read through these problems that you know how to solve them for the future units that are going to come up that are actually along the same lines of what we're talking about today, okay? So what I want you all to do, of course, you need a calculator because we're going to be doing some calculations today. And when we do these problems, this is where you guys got to go in, read the problem, identify what you need in order to solve the example, okay? So, all right. So I'm going to start us off here, okay, with the first example. So in talking about solute calculations, we discussed yesterday that solutes are typically like salts, sugars, things that can break down and ionize in water, namely, okay? Then you have your solvents, which we know water is the universal solvent. Water is a solvent in a lot of these problems that you guys will see. So when you put the two together, you end up with calculating either your solute or, either end up calculating either your molarity or your molality or both. It depends on what they're looking for, okay? Now, I am going to go through these examples with you, and as I teach this lesson for this afternoon, keep in mind that everything that you do today will affect you a month from now because everything builds upon each other, all right? So, let's go ahead and get into this first example. In this first example here, I want you to identify the components. This is a thing where a lot of my problems, I try to break them down to where if you get the first step, you'll get the second step. It'll lead you to the third step because you got to know how to solve the problem. If you don't know what the solute is, you're not going to know what anything else is, okay, within your example. So here's the first problem. A student dissolves 15.0 grams of sodium chloride in 250.0 milliliters of water. A, identify the solute. Well, in this particular case right here, the solute would be the 15.0 grams of sodium chloride. It is usually a solid that can be dissolved. Okay, so that is our solute. Letter B says identify the solvent. Well, the solvent is what is actually going to be used in order to dissolve your solute. So that is your solvent. Now, for your solution, okay? For your solution, identify the solution. It's both of these together, okay? That gives you your solution. That's it. That's all. Nothing more, nothing less. Now, if I wanted to take this problem one step further and say, all right, matter of fact, let me go ahead and type this in now, okay, because we're going to actually take this one step further. I want you to calculate, oops, got my all caps on. Okay, calculate the molarity of this solution. Now, in order to do that, you will need the molar mass, okay, of sodium chloride. And I'm going to go ahead and tell you what that is because this is a number that's in my brain cells, okay, because I've been, using these numbers for a very long time. So it's 58.45 grams per mole. Okay, that is the molar mass for sodium chloride. Now, here is the thing. Whoop. Hold on, y'all. Okay, but here is the thing. When you do these problems, okay, I want you guys to keep in mind that each of these examples here are built upon one another, okay? Meaning when you do the calculations, you want to make sure that you're able to identify the pieces of what you have within your problem. Okay, so I'm going to go ahead and I'm going to take the 15 grams. And by the way, let me go ahead and give you all the formula. Molarity is equal to moles per liter. Okay? Molarity is equal to moles per liter. So if you know that, okay, if you know that molarity is equal to moles per liter, do you see the moles anywhere in your problem? No. But what you have to do is take the 15.0 grams of sodium chloride and convert that to a mole. You also know that because I said moles per liter, you have to take the 250.0 milliliters of water. You've got to convert that to a liter. So those are the two things that you have to do in this particular example right here. So now I'm going to go ahead and do both of them. I'm going to go ahead and take the 15.0 grams of sodium chloride, and I'm going to convert that to a mole. 1 mole of sodium chloride is equal to the 58.45 grams of sodium chloride, which is the molar mass or the weight, okay? So I'm going to go ahead and cancel out my grams, and this number here needs to be in 3 significant digits, okay? Now, again, for those of you all that are here, this is for General Chemistry 2 students, so just FYI, this is General Chemistry 2 information. I'm going through steps that I feel you should already know, okay? Hint, hint, that you should already know. So right here, I get 0.257. 0.257 moles of NaCl. Now, here is the other thing that you have to do within your problem, okay? The other thing that you're going to have to do is just simply divide this number by liters. So in order to convert my 250 milliliters to a liter, I know to either divide that 250 by 1,000 or just move my decimal back 3 places to the left. So I already know what it's equal to. So that's why I'm putting the number down right here. Okay? So here it is right here. And now, let me make sure you all can see the whole board. Hold on, y'all. Make sure y'all can see the whole thing. Okay, there we go. Now, here's the catch. Being that my volume was in 4 significant digits, I mean, you could put the extra 0 on the end if you want to, but it's not necessary because at the end of the day, your final answer is still going to have 3 significant digits because of the smallest amount of values, okay, of numbers that you're supposed to go by. So I'll just put that there just so you all can see that. So 0.257 divided by 0.2500 gives me 1.028. But we know that because we've had chemistry before, our final answer should have 3 significant digits. So 1.03 molarity. That is the answer there for this particular problem. Okay? That is the answer for this particular problem. Although they did not ask us to do that, that was something that I added to the problem so that you all could see how simple this is. Okay? Now, we're going to go ahead and move to number 2 now. Number 2, it says mass percent. So this is another type of formula that you all have to be familiar with in your General Chemistry 2 classes, okay? So with mass percent is just W by W. That means weight by weight, okay? Weight by weight. So I'm going to go through this example with you. And if you all have questions, let me know. But this particular problem is pretty straightforward. Okay? Make sure that you all continue to tap the live out and share this live out with anybody that you feel would benefit from this particular conversation. All right. So for this example right here, because the mass percent, okay, is equal to the grams of your solute divided by the grams of your solvent times 100%. This particular example, guys, is straightforward, okay? It is straightforward. So all you have to do here is plug in the numbers and keep it moving, okay? So I'm going to go ahead and plug in the numbers that I already know based on the problem. So right here, I'm going to say the solute was 8.0 grams divided by 92.0 grams times 100%. Let's see what we get. So 8 divided by 92.0, okay, times 100. This tells me that 8.7% of this solution has sodium chloride in it, okay? All right? That's what this tells me. It tells me that the mass percent of sodium chloride in this solution is 8.7%. All right. Good afternoon, everybody. Welcome to the live. Thank you all for coming in. We're doing General Chemistry 2 stuff. For my chemistry students that are taking General Chemistry 2 this semester, this is one of those conversations that you guys are going to have over the next 2 to 3 weeks. And these are calculations for properties of solutions, okay? So what we're doing here are some problems that you guys are going to experience through the first part of the semester. All right, now, molarity calculations. Again, this is the same thing that we already did actually a few minutes ago when we started out our conversation in problem number 1. So now in problem number 2 now, you're going to have to calculate the molarity. Now, well, here's not the molarity, excuse me. You got to calculate the moles. And it says, how many moles of glucose are present in 500.0 milliliters of a 0.750 molarity glucose solution? All right, here is what you need to do. First off, I know that the formula for molarity is equal to moles divided by liters, right? Well, to calculate my moles, though, it's going to be equal to molarity times the volume, which is liters. You'll need to convert your 500 milliliters to a liter, which is equal to this number right here, okay? 0.500 liters. All I did was divide that by 1,000, but I know what milliliters is equal to a liter because of doing conversions a lot. Now, in this problem, okay, since you're calculating your moles, what you're going to do, you're going to take that formula and you're going to say, all right, well, moles is equal to molarity 0.750. Now, I'm going to replace the M with these units right here. So rather than me putting the M right there, I'm going to put moles per liter in its place. And then I'm going to put the volume 0.500 liters there because you know what's going to happen? You want your L's to cancel out. If I would have put a big M right there, some of you all would have forgotten, well, how did I get a mole out of that? This is what I'm doing here. This is why I'm replacing the units for the proper one so that you can see how we got rid of them. So now, 0.750 times 0.500 gives me 0.375. Okay, so the moles here for my answer, okay, becomes 0.375 moles of glucose. Okay, that's it. That's all. All right. Yep. Divine elegance. You got it right. That is correct. That is correct. Okay, now let's take a look at the next example, okay? Again, these are all the types of problems that you guys are going to experience in General Chem 2. So thank you guys for coming in and joining the live. Make sure that you all continue to tap the screen so that it just resets the algorithm to let everybody know that Professor TK the Chemist is doing chemistry tutorials for students that need extra help. All right, so make sure you all tap that screen. Tap, tap, tap. Thank you all so much in advance. For this next problem, we are trying to solve. Thank you, Tree. Appreciate you. What I want you all to see is that when you guys are actually, okay, good. My vintage K, you're in the right space then. You're in the right place and space. Make sure that you guys are also following me on my YouTube channel where I upload these lives so that if you have to take off, you can at least go back and rewatch the video. All right? Now, for this problem, because you're solving for volume, again, if we go back to our base here, the main formula, molarity is equal to moles divided by liters, then what you have to do is rewrite this and say, all right, well, liters, which is the volume, is equal to moles divided by molarity, okay? See, guys, if you know one formula, everything else will pop up along the lines of each of your examples. So, in order to find this, though, I don't have to do any conversions. None at all. Matter of fact, moles here, because it says what volume in liters of a 2.00 molarity KCl solution contains 0.600 moles of KCl, the moles of KCl goes right there on top. The molarity goes right there on the bottom. Again, I'm going to replace the molarity unit with moles per liter instead of putting the big M there. And then my mole units are going to cancel out. And so now all I have to do is just say 0.600 divided by 2.00 and I get 0.300 liters. Okay? As my final answer. Yes, good job, Divine Elegance. Good job. All right. Now, so far we've done 4 problems. For the past 15 minutes or so, we've done 4 problems. Does anybody have any questions or anything, okay? Listen, Main Street, I teach my students to know those sig figs because this plays a role in your homework. Every time you do homework problems, you'll end up in trouble if you don't know those sig fig rules. And so many students email me every day. Why did my answer come out wrong? Because of those significant digits. And Divine Elegance, you said this is your favorite subject. Okay. Clock that. All right. Okay, zoology. Okay, it took you 2 courses to get sig figs. You know what? It be like that sometime, okay? It bees like that. Sometimes you don't always catch it, and it's okay. But you got your degree now, so you ain't got to worry about it, right? All right. Now, in question number Hamdia, if you're talking about for the TEAS exam, I actually have a class with all that information in there. And if you click the link in my bio, it'll take you straight to it, where it'll actually cover all the things that I don't cover in the live at that time. So when do you plan to take the TEAS exam? And actually what we're doing is technically part of the dimensional analysis. It's just in an indirect way. So now on this next problem with dilutions, it says a nurse needs 250 milliliters of a 0.100 molarity solution, but the stock solution available is 1.00 molarity. What volume of the stock solution is needed? Now, in a problem like this, what I already know, this is a dilution problem. A lot of nurses come across this all the time. There you go, 3D11. Honey, you already know the deal. M1 times V1 equals M2 times V2. Now, anytime you see a problem that says of 250 milliliters of 0.100 molarity, because those two go together, you're going to multiply them and then divide by what's left over. I'm going to say it again. When you see a problem like this and you see the word of, that means they go together, and you're going to multiply those two and divide by what's left over. So, excuse me, in this case right here, what I need to do is, and just FYI, this is the first volume reading, V1. That is your molarity reading, first molarity reading, M1. This is your second molarity reading, M2. So what you're looking for is V2. So to find the formula for V2, I'm just going to divide both sides by M2. And here's the formula here. V2 equals M1 times V1 divided by M2. Okay? That's the formula that you're going to use for this problem. The easiest thing, though, is just to multiply those two numbers that I said go together and divide by 1.00. But in case you didn't see that, I'm just going to go ahead and do it for you. So my M1, molarity 1, is 0.100 molarity times 250, 250.5, excuse me, 250.0, tongue-tied, milliliters. And then you're going to divide that by 1.00 molarity. Thank you, Hamdia. Sister Valentina. I go live Monday and Tuesday at 10 a.m. for General Chem 1 students, 7 p.m. for General Chem 1 students, 12 noon Eastern Standard Time for General Chem 2, and 8:30 for General Chem 2. So if you're getting information for General Chem 2, you can come in on Mondays or Tuesdays at 12 noon and 8:30. So now I am going to cancel out my molarity right here. See that? And now go ahead and plug this in. 0.100 times 250. And then, if you just divide that by 1, you're still going to get the answer. You're welcome, which is 25 milliliters. Okay? 25 milliliters. That is your answer right there. Oh, thank you. We're already at the 10,000 hearts. Thank you, guys. And yes, okay, sig figs. Let's put it in 3 sig figs. Thank you for bringing that up. Thank you for bringing that up. In chemistry, if you see this 25 right here, that's only 2 significant digits. So you need to make sure that you put it in 3, which is just going to simply be to put the extra 0 on the end. So 25.0 milliliters. Okay. All right, Safa, you said go over number 4. Let me see. Okay, what happened with number 4 that you need me to go over? Or you just wanted to see it again? Okay. All right, now make sure you screenshot. Okay. Now, are there any other questions from anybody before we move on to number 6? Any further questions? Okay. We're going to keep it moving. Keep it moving. Now, number 6 deals with molarity from mass. Okay, this particular problem right here, molarity from mass. It says a student dissolves 12.5 grams of calcium chloride in enough water to make 350.0 milliliters of solution. Calculate the molarity. All right. Now, one thing I know, because molarity is equal to moles per liter, okay, I'm going to write that down again. Molarity is equal to moles per liter. There's nothing up here that represents a mole. But what I do know is that I have to convert that to a mole, the grams of calcium chloride. Now, in order to convert the grams of calcium chloride to a mole, I do need the molar mass of calcium chloride. Now, in case some of you all forgot, good job, Salphi. The easiest thing to do is to find the molar mass, okay? And since you guys are in here for General Chem 2, I'm going to assume that you already know how to find the molar mass. The molar mass is 110.98, okay? 110.98. So I'm just going to plug that number into our problem right here, okay? 110.98 grams per mole. Now, I'm going to take that 12.5 grams of CaCl2 and convert that to a mole. And again, because you are in here, I'm assuming that you already know how to convert grams to moles by dividing by the molar mass of calcium chloride. And I'm going to go ahead and cancel out my like units, okay? So 12.5 divided by 110.98 gives us, in 3 significant digits, 0.113 moles of calcium chloride. Now, the other thing, because you have to also make sure that your volume is in liters, this right here is equal to 0.350 liters. The 350 that they gave us, you just divide that by your 1,000, or just know to move the decimal back, okay? All right, so now I'm going to take those two numbers, those two red numbers right there, and I'm going to divide those two out, okay? So right here, let me go ahead and erase this spot right here so you all can see that, okay? So we can have some space right here. And I'm going to write it in a different color too so you all can see that. So to get the molarity, it's going to be the 0.113 moles divided by 0.350 liters. And let's go ahead and divide those two numbers as well. So 0.113 divided by 0.350, and that gives us 0.323. 0.323, and the big M for molarity. Okay? Any questions about that particular problem? All right. Oh, thank you, Aiden. Appreciate you. Now, here is a multiple choice question. Okay, because, we got to, chop some things up. So here is your multiple choice question right here for number 7. Okay. It says, which of the following best describes a solution that contains undissolved solute at the bottom of the container? Now let me give y'all an example. So if I am making iced tea, right, or tea, okay? If I'm making tea or Kool-Aid, and I have a bunch of water in there, right? And then I put a whole lot of sugar, to the point where all of that ain't going to dissolve. How can I best describe the solution? Unsaturated, supersaturated, saturated, or dilute. Now, I'm going to give you a hint. Whenever you have multiple choice questions, you always know that there will be two answers that don't make sense. Now, y'all know good and well this is not unsaturated, nor is it dilute. So it could be super saturated or saturated. And I see two answers in the chat box. I see B and I see C. I see B and I see C. All right. Now, let me give you a hint. Well, first, I'm going to let y'all continue to debate the answer in the comment. Now, Ivelisse, why did you put A if we scratched out A? Think about it. Think about it. Yeah, we are going to get this. You're absolutely right about that. Now, let me tell you all the difference between the two, okay? Because saturated versus supersaturated, there is a difference. When you have a saturated solution, that's when it contains the maximum amount of solute, okay, that can dissolve in the solvent at any given temperature. No matter what the temperature is, the solvent has done all that it can do, okay? The extra solute will not dissolve, and you might see some undissolved solute settling at the bottom of the container. But now, when you have a super saturated solution that contains more solute than normally allowed, okay, at any temperature. So here's some key signs to let you know that the solution is supersaturated. This is when you have crystallization that forms, okay? So when you heat it and you have some of that stuff that's settling at the bottom, if the keyword says, and then crystals are produced, then that tells you that it would be super saturated. So the answer to this question is letter C, saturated. And I like the way you put that, Dante Williams. Yep. That's right, 3 to 11. That's right. Yesterday I did say supersaturated equals crystals. And in this problem, they did not mention anything about the crystals. Okay? So therefore, you know the difference, okay? I'm glad y'all got this right. Good job, good job, good job. Okay, y'all are on it. Y'all are on it today. Okay. Let's move to the next problem. And again, we're trying to make sure that you all know that in chemistry, it doesn't have to be difficult, but you do need to know how to solve the problems according to the pieces of information that is provided, okay? Now, this next one, parts per million, this is going to be Goldilocks. Well, you say it's not dissolved, so it's got to be saturated. Well, it's going to dissolve. Well, okay, yeah, but what you're saying, yeah, it's not all of it's going to be completely dissolved because it's still going to have some left over that remains. So like that like having a heavy hand on them scoops of sugar that you're putting in your tea or your Kool-Aid, okay? Now, if crystals start to form, then you know you're probably making crystal candy. What's that? Rock candy. Rock candy. That's how rock candy comes about, because that's a supersaturated solution. Yep. Okay. I love y'all's questions and comments. Those are very helpful, as we do our discussion. And thank you guys so much for joining the live. Those of you all that are here, you're not here by happenstance. You are here because you want to learn, or you just love chemistry and you just want to build with me. Whatever the case may be, hey, we in it together, okay? So even though the sugar dissolves, you can still taste it. It's still saturated. Yes. Now, if you let that stuff sit and as it cools down, if you start to see crystals forming, then that's super saturated. Okay? Then that's super saturated. Okay. Here is number 6. I know the request was to go back to number 6. Okay. Okay, you're welcome. Now, y'all know we're going to do some more examples, right? Because again, let me tell you, if you start off on the right track for your first chemistry test in General Chem 2, that sets the tone for the semester. And it sets the tone in a good way, because then you don't have to work as hard in terms of trying to figure out how am I going to get a good grade on the next test and the next one. Because I ain't trying to be funny, but it gets a little more intense throughout the semester for General Chem 2, because it's a lot of math, a lot of heavy math. They all have steps to them. And because of all the multiple steps that you have to do, it can cause you a little headache. But just remember, this is just a temporary situation for 16 weeks, okay? That's it. It's temporary. The headache is temporary. Okay, y'all. Okay. Y'all ready for the next ones? Let's go back up here to we're on number 8, parts per million. Now, let me tell y'all how you've heard this phrase before with parts per million. Parts per million comes into play because when we talk about the water system being jacked up because of people putting all these chemicals and poisons in the water, it's because of parts per million, where they're trying to figure out how many parts per million of a certain contaminant is in the water, okay? And because it's a lot, they use this particular calculation here, okay? So it says a water sample contains 3.5 milligrams of fluoride in 2.0 liters of water. Calculate the fluoride concentration in parts per million. Assume that the density of water is 1.00 grams per milliliter. Now, there's a lot packed into this problem. Okay? There's a lot packed into this problem, but you know what? We're going to get through it. We're going to do it. We can do it. So, what you're going to have to do for this particular example is know what is the formula for parts per million. It's just simply milligrams per liter. That's it. That's all. Okay? Parts per million is just simply milligrams per liter. So it's the mass of the solute divided by the mass of the solution, okay? Like, you'll see different formulas for different things, all right? And I'll break it down for you all. Okay. When you talk about parts per million, it's used for water quality, healthcare labs. I'm going to give you all the formula, but I'm going to explain how the formula is actually derived, okay? Because there are two different ways I want you all to look at this problem, okay? And let me see if I can enhance this a little bit bigger. Let's see. Hold on, y'all. Let's see. Okay, I think that should be Big enough for you all to be able to see that, okay? Now, for parts per million, there are two different ways in which you can actually do this problem. If you're given the mass, okay, you're going to use this particular formula when the mass is given and the solution is not water, okay? And you don't assume that the density of the water is 1.00 grams per milliliter. So let me show you what I'm talking about, because there are two different formulas, but you have to know when to use it, okay? So oh yes, okay, yeah, of course, Main Street, of course. Okay. So, now I'm going to explain to you again what this first formula means, okay? So you see where it says parts per million equals mass of solute divided by the mass of the solution times 10 to the sixth power. You use this formula when you are given masses. And when the solution is not water, okay, you use this particular formula when you are given masses. Now, when you look at this formula though, or you look at the problem, I see volume. So because I see volume, I'm going to have to use this other formula that I'm going to tell you. And this only works because the solution is in water. The density is 1.00 grams per milliliter. So I'm going to tell you all what formula to use in this case. And it's milligrams of solute divided by the volume of the solution in liters. Okay? So parts per million is the milligrams of the solute divided by the volume of the solution. Okay? You're going to use this particular formula right here because I see a gram unit and I see a volume unit. I'm sorry, milligram unit and a volume unit. Just divide those two numbers. Okay? Just divide those two numbers. So now what I'm going to do is show you how to do it. Okay? It's real simple. Real simple. So up here, the milligrams was 3.5 for the fluoride, and divide that by 2.0 liters of the water. Okay? And just say 3.5 divided by 2.0, and I get 1.75. Okay? 1.75. Now, here's a sig fig rule. Let me go through this. There are two sig figs in the top number, two sig figs in the bottom number. So even though I get 1.75 parts per million, you need to round that off to 1.8 parts per million. Okay? Because you have to have two significant digits in your final answer. Okay? Any questions? Okay. All right. Y'all know we're going to do what? Keep it moving. All right. Here are two questions for you. And let's see what you guys know. Okay? Number 9 and number 10. Number 9 and number 10. I want you to put your answers in the comment boxes. We're just checking to make sure you understand the vocabulary. All right? So do number 9 and number 10. Let's look at number 9. And again, put your answer in the comment box once you know. Which factor increases the solubility of a gas in water? So if you were in class yesterday, you should know this, okay? Oh, thank you, Main Street. Appreciate you. If you increase the temperature, will that increase the solubility of a gas in water? Or what about if you decrease the pressure? Or increase the pressure? Or just stir the solution? Which one are you going to put for your answer for number 9? So I'm going to give y'all a moment to think about it. So I do see one answer in the comment box. What does everybody else have? For number 9. Again, what factor increases the solubility of a gas? Okay. Remember, to increase the pressure, okay? If you increase pressure, that means you have a higher solubility. And again, the science behind this is Henry's law. Remember the example I gave you all about opening up a can of soda? Okay? So for gases dissolved in liquids, higher pressure means you have higher solubility. Okay? And this is because pressure pushes more gas particles into the liquid. And that's what keeps them there. All right? All right? So if you put some pressure on it, that gas will sit down and stay, according to Henry's law. And Henry's law explains about the solubility of the gas and the pressure and all that good stuff. Okay? So as the pressure increases, your solubility increases. Now, if you increase the temperature, then there will be a decrease in your gas solubility. So that means, like, if you take out soda and you open the can, and you had it in your refrigerator and you open it up and then you let it sit out at room temperature, you wonder why your soda goes flat? It's because the gas is escaping. Warm liquid lets the gas escape more easily. So when you increase the temperature, then the gas solubility decreases. So think, cold refrigerator to room temperature. It's probably warmer in your room. So that's why your soda goes flat, and that's why cold drinks keep their fizz. So there is chemistry in that can of soda. Okay? Okay? So yes, the answer to this question is letter C. Increase the pressure. Okay. Any questions? Okay, what happened when the pressure is decreased? Okay, so let's talk about that again. Okay, let's say that part again. All right, so here's how I want you all to remember. You're welcome, mind, body, beauty. You're welcome. Okay, here's what I want you to do. Remember, if the pressure goes up, the solubility goes up. If the pressure goes down, the solubility goes down. If the temperature goes up, the solubility decreases. Okay? Okay, good. You got it. Okay, good. So pressure go up, solubility goes up. Pressure go down, solubility goes down. Temperature go up, the solubility goes down. Okay? Yes. And yes, 3D11. And this is also similar to Um, Boyle's law, well, more like the combined gas law, but like Boyle's and Charles gas law. Pressure go up, the volume goes down. This is what Boyle's law. Temperature go up, the volume goes up. That's Charles gas law. So a lot of these gas laws come back in part two or General Chem 2 conversation. And stirring, no effect on the solubility. Okay? And then if you speed stirring, I mean, you might end up increasing bubbles, because you flopping it too much, kind of like shaking it up or stirring real fast, but it really doesn't have an effect on the solubility per se. So remember, gas dissolved in a liquid, that means pressure up, solubility is up. Okay. Now, number 10. That was our last question. Yes, number 10. Which statement is true? The solvent is always a solid? Man, Solvents are liquids. Okay, I'm just telling you to get rid of that one. Letter B. The solute is present in the greatest amount. A solution is a homogeneous mixture. Or solubility is independent of temperature. Okay. And this one for number 10 should be really straightforward. And you should say C. Yep. C. Okay. Any questions? Now, you know what? I've got time to go over a few more problems that I wanted to plug in here, okay? And because I know, when you come in, you want to make sure that you got all these questions right. And I got you. We'll close out on these next two problems. And I wanted to give you all some more mid type questions, okay? So here is your next question right here, okay? And whenever I design my questions, I like to have them based on higher order thinking, because again, some of them can be very basic, but then I know when you all take the test, if you didn't have a challenging problem during class, it might be a challenge when you take the actual test. So some of these questions are going to be a little more intense, okay? So read between the lines. All right, read between the lines. So this next question right here, it says, a student prepares a disinfecting solution by dissolving 18.0 grams of isopropyl alcohol into 82.0 grams of water. Identify the solute, identify the solvent, and explain why water is considered the solvent even though isopropyl alcohol is a liquid. Now, y'all know it's that time of year, depending on where you all live, you may see some TikToks talking about putting alcohol and water in a container and put that on your windshields. I'm going to do a little deep dive on that. I'm going to come back and do a story time on that. I'll post that, whether or not that's true, the chemistry behind it. So I'm going to let you all do number 10. This is going to be like number 11. Okay? This should be straightforward. You should be able to get this really quickly. You all know that the solute in this case is the isopropyl alcohol. The solvent, the universal solvent, is the water. Okay, so the solute, let me put that in two different colors so that way you all can see the difference, okay? The solute is the isopropyl alcohol. The solvent is the water. And why is water considered to be the solvent even though isopropyl alcohol is a liquid? So let me hear what you guys got in terms of your answers. So you all can put your answers in the comment box. Okay, but why, Safa? But why? And from the other students, can y'all tell me why? Tell me why. It's really easy to see. Don't think too deep about it. Which number is greater? The one that you have more of will typically be the one that's going to dissolve the most of the other thing, okay? Hint, hint. So it is because, to answer the letter C, it is because you have more water than you do of the isopropyl alcohol. Therefore, it's pretty much like it's washing it out, okay? So you have more water, way more water than you do isopropyl alcohol. So it's almost like it's diluting it out. So it's almost like when you make like there's 70% alcohol. You know, you make, if you go to the drugstore and you see 70%, this is usually volume by weight, I believe, and then you may see 90%. Okay, this is the one you want to kill more of those germs. Okay, the 90%. Yes, because we have more water. Okay. All right. Oh no, that's okay. That's okay. Sometimes we think more than what we, think harder, but that's okay. That is okay. All right. We're gonna do number 2 right here, okay? And we're gonna close it out with this one. You've got mass percent problems. And then you got a little extra with it. It says an IV saline solution is prepared using 9.00 grams of sodium chloride mixed with 491 grams of water. Calculate the mass percent of sodium chloride. Part A. And in part B, is this solution more concentrated or less concentrated than a solution that is 1.5% sodium chloride by mass? Now, to answer this question, all you got to do, first you got to do part A, because you don't know the answer until you do part A. So what you're going to do here, you're going to divide these two numbers that I'm highlighting. Divide, because remember, this is a weight by weight percent problem. So to get your mass percent, you're going to say 9.00 grams of the solute divided by 491 grams of the solvent times 100%. So let's plug this into our calculator. So we've got 9 divided by 491 times 100%, and we get 1.83%. So here is the question. Is this solution more concentrated or less concentrated than a solution that is 1.5% sodium chloride by mass? So they want to know, is this solution right here, this number that we just calculated, is it more concentrated or less concentrated than that 1.5? And it's real easy to see. More concentrated. Okay? Chemistry doesn't have to be difficult, y'all. See that? There it is right there. Okay. All right. Okay, but so before we close out, does anybody have any other questions or concerns? Because FYI, I will be back on tonight at 8:30 p.m. So those of you all that want to get some additional help, you can come back through at 8 p.m. Eastern Standard Time, and I got you guys covered with more of these types of problems for General Chemistry 2 students, okay? So I look forward to seeing you guys. Make sure that you guys bring your dinner back tonight, okay? At 8:30 p.m. Eastern Standard Time, all right? So if there aren't any other questions, you guys take care.